In this problem, we are going to solve a free response question on projectile motion. A student conducts an experiment on projectile motion. She launches a ball using projectile launcher and launches it at an angle of 30 degree, as we can see in the diagram. So the initial velocity is v0 and the angle is 30 degree. The data is also given to us in the table here. The question is asking us to determine an equation for vertical position, that is y, of the ball during its motion. Express your answer in terms of x, v0, theta and physical constants. So because the question is asking us to calculate or to get an equation for y, we will use the kinematic equations for the vertical motion. So y or delta y is equal to vit plus half at square. Now in the projectile, we need to resolve the initial velocity for vertical and horizontal. So for vertical, it will be v0 sine 30 and for horizontal, it will be v0 cosine 30. So we can write delta y is equal to v0 sine 30 multiplied by time minus half gt square. Why minus half gt square? Because acceleration will be acceleration due to gravity, and we know that it's always acting downwards, so it will be negative g. Now we have got in the equation what is required, that is v0, but still we don't have x and theta. Instead we have time. Instead of that we have time. So we will replace that time using the horizontal motion. So in horizontal direction, we know that horizontal distance is equal to horizontal velocity multiplied by time of flight. Horizontal distance, let's write that as x. Horizontal velocity, from the diagram we can see that it is v0 cosine 30. So v0 cosine 30 multiplied by time. So we can rearrange this equation and we can write as t equal x over v0 cosine 30. Now I'm going to replace this in this equation so that we can get what they are asking us to get in the equation. So we'll write that delta y is equal to v0 sine 30, then x over v0 cosine 30 minus half g x over v0 cosine 30 square. v0 and v0 can be cancelled and sine over cosine is tan, so I can write x tan 30. Just to recall again, tan theta is sine theta over cosine theta. So I have here sine 30 over cosine 30, which I can write as tan 30 minus half g. I'll open the bracket for the square, so x square over v0 square and cosine square 30. If you want, you can keep the bracket closed, that's also fine. But we have now got the equation for delta y, that is the vertical position, in terms of x, v0 and theta. Okay, we can do one more thing. Theta is not there yet. We have got here instead of theta I have got 30, so I can rewrite the equation just replacing 30 by theta, so that that also becomes a variable. So this will be x tan theta minus gx square over 2 v0 square cosine square theta. Now we have got everything what the question is asking us to get. Calculate the launch velocity using the data for range. So we have got the data. So the student was doing an experiment and she did it 6 times and got different values for range. So now we want to find what's the value for the launch velocity from this range. So how to get that? We can see that we have got an equation in the first part. So I'm just going to copy that equation onto the next page. So let's just get that equation. Delta y is equal to, let's see what was the equation, x tan theta minus gx square, x tan theta minus gx square over 2v square v0 square cosine square theta. So 2v0 square cosine square theta. Now if it's the range value which we are looking at, we know that the projectile will be launched from the ground and it comes back to the ground. So we know that delta y will be equal to 0. And x will be the range itself. So we have got 6 values for range from the data. So we need to find what's the average of it. So I'm going to add all of them. And then divide it by the number of observations which I've got, that is 6. So that value, let's just calculate. 6.92 plus 7.01 plus 6.89 plus 7.24 plus 7.12 plus 7.09. And then I will divide that by 6. I get the answer as 7.045. That's the value for the average value for range which I get. So that's the value for x. I can substitute that 7.045. Then tan theta is the launch angle which was 30. So tan 30 minus g x square. X is 7.045 whole square over 2v0 square cosine square. So we replace the angle with 30 and g, the value of g I have replaced with 9.8, and then you can solve it for v0 using your calculator. You'll get the answer as 8.93 meter per second. Next, we want to find the height of the projectile from the point of launch where it has traveled a horizontal distance of 4.01 meter. When it has traveled a horizontal distance of 4.01 meter. So as the projectile travels, so it's asking you when it has traveled a distance of 4.01 meter, what will be its height? So for that, again, we will go back to the equation of delta y which we got from before. Delta y is equal to x tan theta. Let's just write that, x tan theta minus gx square over 2v0 square cosine square theta. That's the formula the equation which we got in the first part. Now we want to find what is delta y, and we have been given that the horizontal distance covered is 4.01. We also know that the angle of launch is 30 degree. There is no change in that. The value for g is 9.8. And now we also know what is v0 from our previous answer, which is 8.93. And we have to just substitute all these numbers into the equation. So 4.01 tan 30 minus 9.8 times 4.01 square over 2 times 8.93 square cosine square 30. And we can solve it to get the value for delta y. So let's just do that. 4.01 times tan 30 minus, then we can start a fraction, 9.8 times 4.01 square over 2 times 8.93 square times, we'll start a bracket for cosine 30, close the bracket for the angle, close the bracket for cosine, and then square. You should get the answer now. That answer for me comes out as 0.99, and the unit will be meters. Now in this last part, student obtains the following data after conducting a video analysis of the projectile motion. So now we have got the value for t, x and y. It's asking you state what should be plotted on x and y axis to get a straight line whose slope can be used for calculating launch speed. So key points here that we want to get a straight line, and second, we want to use the slope to get the launch speed. So now we have two equations which we got from the first part. So if you go back to the first part, you can see that we had this equation, x equal v0 cosine 30 multiplied by time, as well as the equation which we actually derived. So I'm going to use this equation because that's the easier one to plot. So let's see if I write that here. X equal v0 cosine theta. Instead of 30, I'm going to write theta multiplied by time. So now actually we can write it as 30 because she did not change the angle. So we can just write that as 30 cosine 30. And then now we want to see what is the data given to us. Do we have the data for time? Yes, we have the data for time. We also have the data for x. So if I plot, so straight line equation is y equal mx. That's the equation for straight line. So if I plot on y axis, that is the vertical axis, on the y axis, if I plot x, which is this, and on the x-axis if I plot time, I can see that I will get a straight line because this equation is in the format of y equal mx plus c, where m is equal to v0 cosine 30. That means the slope is equal to v0 cosine 30. So I can use the slope to get the launch speed, which is v0, which is the launch speed, will be equal to slope divided by cosine 30. So if I plot a graph between x and t, that is the horizontal distance covered versus time, if I plot it on a graph, the slope of it can be used to find the launch speed.